In the previous module, we have looked at one direction of this equivalence. We have looked at the mixed strategy equivalence of behavioral strategy, and we have actually shown this theorem which gives us a necessary and sufficient condition when this is possible, when you can have a mixed strategy equivalence of a behavioral strategy. So in this module, we are going to discuss the other direction, that is when we can have a behavioral strategy equivalence for a given mixed strategy. And in order to do that, we'll have to do a little bit of formalization. What is the forgetfulness of the player? We have seen that both these cases where the equivalence does not hold, the players have some kind of a forgetfulness. In one case, the player forgets whether it has moved at all or not. In the other case, it forgets which action it picked. And we'll have to systematically take care of these two things. And we'll show a result that it is sufficient to just take care of those forgetfulness. And then you can have an equivalence between these two things. So let us first define the following, which will be useful when we develop this notion of forgetfulness. So this is called the choice of the same action at an information set. So as the name suggests, it is just saying that if you consider two different paths, so x and x hat, one of length k and the other one of length l. So if you consider an information set of player I that intersects these two paths only at one vertex. So path 1, so maybe if you look at these two paths, maybe they are coming in different ways. So this is the path x, and this is the path x hat, and there is one information set of player I, and that is given by iij, and this intersects here at the node x of k, and this intersects the x hat path at x hat of L, right? If that happens, we will call that these two paths choose the same action at information set iij if, of course, k is smaller than capital K and L is small l is smaller than capital L. Then the actions that is leading to xk plus 1. So the next action, so if you look at in this thing, so the action that has been taken, because in the same information set, the action set will also be the same. So the action that has been taken here and the action that has been taken here must be the same. If that happens, then we call that these two paths choose the same action at the information set iij. Okay. So with that definition, so we are just going to use this terminology, choosing the same action at an information set. Now, as we have already said, that leading to may not be a relation between a parent and a child node. It can be any descendant of the previous node, since the path is unique for a tree. Right? Now we can define the notion of recall or not forgetfulness in the following way. So we call player I to have a perfect recall if two conditions hold. The first condition is that for every information set of player I, this intersects every path from the root to a leaf node at most once. Pick any leaf node and look at the unique path that is leading from the root to that leaf node. That should intersect every information set of player I at most once. There should not be any case like the previous one where you had the same path intersecting the same information set of the player multiple times. So note that this is already taking care of the sufficiency condition in the previous theorem, where we had equivalence between, so we had an equivalent mixed strategy for a behavioral strategy. Now we are going to do the other way around. From mixed strategy, we are trying to find an equivalent behavioral strategy. The first condition is this, which actually subsumes the previous condition. Now look at the second condition. What is this? The second condition, it says that if you pick every two path, consider two paths that ends at the same information set for player I. So let's say IIJ, and there are two paths that are ending at the same information set, maybe two different nodes. This condition says that it must pass through the same information sets of I in the same order. So this is very crucial. It should pass through. So if you are at a specific information set at some point, so for player I, let's say II of J, and you are considering two different nodes, and you are taking two different paths which are leading to here, then these two paths must go through the same information sets of the same player and in the same order. So that is not all. The other condition that must be satisfied is that in every such information set, the two paths should choose the same action. So if in this node at a different information set, it has chosen action A, this should also choose action A, because in the same information set the action set should be the same, but it is forcing that you should take the same action. And if these two conditions are satisfied, then we will say that player I has perfect recall. If you do not satisfy this condition, it is giving some sort of a forgetfulness, either in terms of which actions you have picked in the past, or whether you have played at all in the previous rounds. Right? So that is so the first condition is actually ruling out that you forget whether you have played at all or not. The second condition is ruling out that you do not forget. You do not forget what action you have picked. So you may rephrase this the same statement in more formal terms. So let's say I pick a specific information set IIJ for player I, and consider every pair of vertices x and x prime in, that is living in that information set, something like this, x and x prime. Now the decision vertices, so that is those are the vertices where player I is the player, and if you take the sequence of them, let's say it starts from 1 to capital L. There are L such places where player I was playing, and of course this last node is the node X that we have already picked. And similarly, you can pick the sequence of this decision vertices in the other path, x prime path, right? So there the last one is x prime. Then three conditions should get satisfied because of these two assumptions of perfect recall. First, the length of these two paths should be identical. They should not be different. That is actually coming because you will have to go through the same information sets and in the same order. So therefore the sequence, the length should be the same. The second condition is that if you pick the corresponding, so if you pick the lth element from this sequence and the lth element from the same sequence, that element must live in the same information set for player I, right? And the third condition is that they should pick the same action while going from L to L plus 1 in both these paths. Right, so these three conditions together is actually formally representing what is the definition of perfect recall. Now this is perfect recall for player I. Now we will call that the perfect recall. So a game is of perfect recall if every player has a perfect recall. Now this remark we have already made, that the perfect recall's definition, the first condition there already subsumes the condition of the theorem, of the previous theorem, where every behavioral strategy had a equivalent mixed strategy. Right? So this is this equivalence is already subsuming. So perfect recall is actually a more restrictive condition than the previous the condition of the previous theorem. So let us look at a couple of examples to appreciate and understand the point of perfect recall. Let us look at these two graphs. So this is the game tree, and there are 3 players in this first example. 3 moves first, and then depending on which action it picks, it is time for player 1 or player 2 to play. And player 1 and player 2 has one information set. So everywhere, so here these players can play in 2 different nodes, but both these nodes are in the same information set for player 1 and 2. So the other example is a very similar one, but there is no player 3. Instead, player 1 is moving in the first round, right? The graph is very much similar, but player 1 is actually taken the position of player 3. Now you can actually look at the conditions that we have defined for perfect recall, and you can find out, because in this case all those the points of intersecting with other information sets of player 1 does not really occur. This gets satisfied, the conditions of perfect recall get satisfied in this first example vacuously. So therefore this is a game with perfect recall, because every player has perfect recall in this game. But in example 2, player 1, you can notice that player 1 is playing twice. It has 2 information sets. One is the singleton information set, and the other information set consists of these 2 nodes. But if you pick this as x and this as x hat, you can see that there are 2 different actions which are leading to those places. In some sense, it is very similar to the first example that we have given in the previous module, that you have actually forgotten which action you have taken. So the moment you are saying that these 2 nodes are in the same information set, that means player 1 cannot distinguish whether it is in this history of the game or in the other history of the game. That is, player 1 has actually played either this action or this action that this player has forgotten, and that is contrary to the definition of perfect recall. So that is the reason player 1 does not have a perfect recall in this game, while player 2 has a perfect recall, of course. But this is not so, because all the players do not have perfect recall, so this is not a game with a perfect recall. Okay. So let us see what are the implications of perfect recall. So certain good things happen when we have perfect recall, and in practice most of the games have perfect recall, because players do not forget what they have played or whether they have played at all, as long as the game is not too long. So let's say this SI star X is the set of pure strategies of player I, at which he chooses the actions leading to X, right? So simply speaking, this is just the intersection. You list out all the actions or the strategies of player I, which constitutes this set SI, and take the intersection with the path which is starting from the root to X. Whichever you find, whichever action strategy that you find, that is going to be the member of this set SI star X. Okay. Now the first theorem, which shows it is quite obvious once you think about this perfect recall, the definition of perfect recall, that if I is a player with a perfect recall, and X and X prime are 2 vertices in the same information set of I, then this sets SI star of X and SI star of X prime must be identical. So that is the intersections that you will have because of the implications of perfect recall. They should have the same set of elements in both these sets. So here it is written, the hint of this proof is given. So it comes from the same sequence of this information sets and the same actions that has been picked by each of these by the same player. Now, there is another implication of perfect recall, which gives the equivalence of mixed and behavioral strategies. So this is a theorem shown by Kuhn in 1957. So in every imperfect information extensive form game, if I is a player with a perfect recall, then for every mixed strategy of player I, there exists an equivalent behavioral strategy. So equivalent behavioral strategy. This was missed. So we already know that the other thing is this converse is already true. That is, if you have a perfect recall, with perfect recall, you already subsume the condition that you needed for a behavioral strategy to have a equivalent mixed strategy representation. That was the previous theorem in the last module. Then with perfect recall, you can have a equivalence between these two behavioral strategies. Whether you call it a behavioral strategy or a mixed strategy does not matter. With perfect recall, all these things are equivalent, right? Now this also is a kind of a little longer proof, and it actually uses the following idea. So the current statement of this Kuhn's theorem is just giving a equivalence for the mixed strategy. So given a mixed strategy, you are trying to find an equivalent behavioral strategy, and the proof is a constructive proof. You start with a mixed strategy and then you construct the behavioral strategy such that the probabilities of reaching a leaf node are the same. And the arguments essentially show that such a construction is possible, right? So perfect recall is given to you, and you'll just have to construct this and show where this perfect recall is being used. The proof is a little long, that's why I have given it as a reading exercise. So this is the theorem 6.15 from the Maschler's book. So this actually concludes the discussion of the equivalence of behavioral and mixed strategy. So which actually also tells us something that for reasonable games, so in practice we can assume this notion of perfect recall to be quite reasonable. So for those kind of games, we can talk about the mixed strategy and behavioral strategy interchangeably. In particular, behavioral strategies are more natural because it is randomizing at every information set. Therefore, without loss of generality in games with perfect recall, we can talk about behavioral strategies, which is the only randomization policy on this in imperfect information extensive form games.